Okay. Now we continue the class in this session. We finish zero law. I almost say lay zero. Well, zero law and first law of thermodynamics. Now we go to the second law. For understanding the second law, well, there are different ways to explain the second law. And this is where the concept of entropy comes out. Entropy. And for understanding entropy, I will give you a few examples. Before watching the examples that these guys of Maddie's Fund have for us, I will give a few examples in advance. Let's assume that I have a particle in a box here, a small box here, and I have some particle. I don't know where is the particle. And this is not quantum mechanics. So forget quantum mechanics, don't come with that word, jet, not jet. No. Then, of course, there is the particle has a probability to be somewhere, right? Let's assume that I open the box. What will happen? That particle, or all the particles will start to move freely in the room, spontaneously. So we say the entropy increase spontaneously. The process spontaneously increase entropy. So what does entropy measure in that case? When the particle escape, it's more difficult to know where is the particle. So there are more possible available states consistent with the microstate. So my knowledge about the particle conditions decrease somehow. So entropy is connected with that. So once we have a system in some equilibrium conditions, let's put here, I have this box here. And I have some molecules here, some gas here, at some temperature. There are some specific number of configurations, many possible configurations that can make macroscopically this temperature. So the entropy is proportional to the natural logarithm of that. If there is only one configuration, natural logarithm of 1 is 0. The entropy will be 0. That's the absolute 0, which will be the third law of thermodynamics. But let's study the other thing. When entropy, somehow people say, oh, it's a measure of disorder. And also, it's not the disorder that the high school students may or the bachelor students may, especially those of the other schools. Not here. The students here are very well behaved. That's why it's so easy to record here. When I am recording in other classes, I cannot record. I have to stop it because I have to call the attention to many people. That's why. So let's continue here. Why people say it's a measure of disorder? Let's put it this way. I will construct this building. This building before construction was a disaster, was a bunch of sand and mixes, and then many workers came and made this very organized structure. The entropy of this building when it was constructed increase or decrease? Yeah, decrease. Why? It's more organized. Violation of the second law of thermodynamics. What happens? Are we violating the second law of thermodynamics? What do you think? Because the second law of thermodynamics tells us the entropy should increase. But the entropy is decreasing there. So what happened? When we construct a building,
just because entropy decreased locally in the different areas, I mean that overall it has its increase.
Oh my God, that's the response. Yeah, that's true. It means Locally, the entropy decrease, but globally, when you include the surroundings, let's put it this way, the second law is applicable in an adiabatic system. It means you have to select all the surroundings until there is no flow heat in the system. Naturally, let's put different cases. If I have this box and the box emits heat, the entropy inside the box decreases, but the sum of the decrease of entropy plus the increase of entropy here of the surroundings is positive. So there is a larger increase of entropy than what it decreases inside. So the total entropy increase. No? In the case of buildings also, you construct the building with many machines. You made this building very organized, nice. The entropy locally of this building decrease, but you have to invest a lot of energy outside, a lot of disorder you have to make for constructing this organized structure. All those machines working around, they generate, look at that. Can you listen to that song? Can you listen? That's entropy, which goes as energy of the sound, as gas emissions of the machines, etc. And if you calculate the amount of increase of the entropy plus the amount of decrease of this entropy, or minus if you want to see in that way, the total result will tell you, okay, that the change of entropy, people call it the universe. When they call it universe, it doesn't mean the universe. The universe means the locally plus the surroundings is larger or equal than zero. If it's equal to zero, that's an ideal process, of course. But normally, in ordinary processes, of course, the entropy increase. A spontaneous process increases the entropy. Even when you put water here at temperature 30 degrees, and you put an ice 0 degrees, the heat comes from here to here. In this process, the change of entropy is positive. The entropy of this water decreases, the entropy of the ice increases, but the total entropy, the change of the entropy here plus the change of entropy of the water totally is larger than zero. Okay? I put a piece of ice on the environment like this. Ice. On a table, I put ice. What will happen with the ice? Melt. If the temperature of the is 30 degrees, it will start to melt. But before that, the ice has a very organized structure, no? Not perfect, but organized. It means you can more or less identify some crystals. The molecules of water are there in a very organized arrangement. So it's a system with low entropy. There is a vibration, there are vibrational modes and so on that contribute to the entropy, but still is a relatively small entropy compared with the gas or compared with the. When the ice becomes water, like this, in a tank, now it's more difficult to locate the molecules. If you want to locate one specific molecule, is more difficult because it can move more freely. The entropy increase. The possibilities for that molecule to occupy certain positions increase. That's an increase of entropy. Now, if you start to input heat here, and it becomes vapor, it evaporates. Then what happened? The entropy increase also, because now it's even more difficult to locate one molecule of water. There are more, the molecules have more chances to occupy whatever they wish. So this is an example of how the entropy operates. Or the measure of disorder. And as I said before, if I throw this marker to the floor, boom, the energy is not wasted. The energy is transmitted to the floor in the vibrational modes of the material of the floor, but it dissipates among many degrees of freedom compared with the small amount of degrees of freedoms I am considering here. So in that sense, the entropy increase. Okay. The entropy is well defined in statistical mechanics. In statistical mechanics, unfortunately, or fortunately, depends on the point of view, because some students don't want to know about that. But normally in statistical mechanics, you study these things properly. And statistical ensembles, the microcanonical ensemble, the canonical ensemble, grand canonical ensemble, and how to calculate properly the thermodynamic properties of any system and how to include the quantum effects also. Because something we will see later is that a parenthesis here for talking a little bit about quantum mechanics, because I like to mix up this thing, is that there are ways to measure the heat capacity of the systems based on the number of degrees of freedoms the molecules have. For example, if you consider a single atom, it's not the same as a molecule, because the molecule rotates, vibrates, and so on. Of course, it will have a different heat capacity. If you put this atom in a molecule, as a molecule will behave different as an individual atom. But it can now, in the past, when people calculate the heat capacities, they use the equipartition theory. Classical, which is a classical assumption, equipartition theory suggests that the energy distributes equally among all the degrees of freedom. For example, if a molecule can rotate, vibrates, or whatever, people assume all the energy is distributed equally in all those degrees of freedom, vibrational, rotational, and whatever else. But it came out that sometimes, particularly at low temperatures, the equipartition theory failed. And guess what happened? It's because some degrees of freedom fell asleep at some temperature. They are not activated, and that's a quantum effect. This is where quantum mechanics. So you can see quantum mechanics is the most useful thing which happens, well, with relativity and so on. But quantum mechanics has applications in everywhere, including our current technology. So coming back to the definition of entropy, look at this table. Many coins here on the table. Of course, many options. And you can count the possible states, of course. The number of tails here, blah, blah, blah. So what they are trying to say here is that when the number of possibilities increase, the entropy increase. I will not go into the details because now this is another example. This gas is inside a balloon. The balloon is inside the... When I explode this, I know the gas is contained here, and there are a certain number of states consistent with the macro state. The macro state is the temperature, the pressure. This is the macro state. So there are many molecules, and they can arrange in many different ways, such that they reproduce temperature, the same pressure, the same everything. And that measures the entropy. Remember, the entropy is proportional to the natural logarithm of the number of states, omega, number of possible states, consistent with the microstate. With the microstate. When I explode this balloon, boom, then the gas expands spontaneously. All the spontaneous processes increase in entropy. The non-spontaneous process, like refrigeration, for example, they decrease entropy locally, but globally, the entropy increase globally. Okay? Then, it's important to have now, when the balloon explodes, the gas expands, then, of course, the molecules have more accessible states consistent with a new macrostate, which can have different temperature, different pressure, because now the gas expands, but still the entropy increase. So the omega, which I just defined now, it becomes larger. This is the case they are explaining here. This is the process They should. The balloon explodes, the gas initially is concentrated here in this balloon. And then after becomes like this, spontaneous. You will never see a spontaneous process to go back. When a crystal, you destroy a glass, let's say, or you throw a glass of water to the floor. Here's the water will spread on the floor. The crystal will explode. Have you ever seen the water coming back and the crystal reconstructed again? No, it never happened. Spontaneously will never happen. And as a consequence that the entropy of spontaneous processes increase. When the crystal explodes, the disorder increase of that material. The water spread farther away, so it's more disorganized system, so the entropy increase. For organizing it, what do you have to do? You have to make some work around, you can reconstruct the crystal, you can melt it, but for doing that, you have to increase the entropy further for reducing that entropy. So that's the issue. In refrigeration, we see that. Spontaneously, and this is the principle how the machines operate. Later in the subsequent session, not this because it's too premature for talking about thermodynamic cycles, but we will see in next session thermodynamic cycles. Cycles, for example, the machines you see in the street, the car, all these kind of things, there's a lot of physics there. Not only thermodynamics, there's plenty of physics there. All the wheels, the traction, whatever. And the engines, the motors, they operate under something called thermodynamic cycles. A cycle, if I complete the cycle, the change of internal energy is zero because it's a cycle. No? Remember that the internal energy doesn't depend, but the others, the work and heat, one will be the negative of the other. No? But the point I want to remark here is that in such a case, I am advancing a little bit, but it's better for you to start to understand these things better. Is that if you have something at a temperature 1, for example, let's assume that this is 30 degrees, and this is 0 degrees here. The heat will flow from here to here. And this is how the motors operate. You will see later. You just put some engine here, and you take advantage of this flow of heat for creating some work here, for making the machine to operate. When you produce electricity, what did I say happen? You have a turbine. Sometimes what they do is a thermoelectric or a nuclear plant. In the nuclear plant, they will not throw you the toxic materials to expand. No, that doesn't happen. The toxic materials, what they do is to heat some camera, and the gas which expands is inoffensive. It's the one which go to the turbines and make the turbines to move. And this can operate spontaneously, of course. In the thermoelectric, what happens is that you put the gas heat and it expands also and move the turbines. In that sense, of course, there is a part of the process is spontaneous and part of the process is induced. But the global change of entropy of this process is positive. You will find that not even the ideal machines have efficiency of 100%. In the next class, we will see what is the Carnot cycle, what is the Carnot efficiency. For refrigeration, we define coefficient of operation, which is different. It can be larger than 1. But you will see that when we evaluate machines, precisely because of the second law, not even an ideal machine can reach the 100% of efficiency. Not even an ideal machine. So we use that ideal efficiency for measuring our real life machines. Yeah? We cannot compare with the 100%. We have to compare with the ideal cycle, which is what the best the machines can do under some conditions. So coming back to the entropy case, spontaneous processes increase the entropy. Nice. Excellent. Perfect. Tremendous. So this is the definition of entropy I said just a few moments ago. I say entropy proportional to the logarithm of omega. But that proportionality, you make an equality, you have to introduce a constant. This is in statistical mechanics, this is a statistical ensemble called microcanonical ensemble. And of course, if omega is 1, what happens? This is 0. Entropy 0, which is the third law of thermodynamics. So I don't have to explain you separately the third law of thermodynamics. The third law of thermodynamics is telling you that when you reach the absolute 0 of temperature, your entropy is 0. Yeah, that's why it's telling the third law of thermodynamics. So in the exams, I can ask you, okay, what does actually the number of the law is not important. Which one is first, second, or third? That's not important because that's historical convention. No? Historically, they define like that, but it could have been the other way around, and nobody cares. What you care is there is a law of thermal equilibrium, which is the 0 law. There is a law of conservation of energy, which is the first law. There is a law of increase of entropy. Spontaneous processes increase entropy. There is a law of absolute 0. When you reach the absolute 0, and now the absolute 0 is measured in kelvins. 0 kelvins is the absolute 0 temperature, which our current technology cannot reach. I think the lowest temperature they have reached, I don't remember what is the lowest. Still is not the absolute 0 for sure, because still there is a lot of vibration of the molecules or whatever you want to say. They move slower maybe, but there is still some entropy there. So coming back to this subject, yeah, those are the laws of thermodynamics. So let's continue here. So this is the entropy. This is the Boltzmann constant, is defined with this. And this is the number of microstates. I always say microstates consistent with the macrostate. So it means that you have a box, again, I repeat, with temperature, pressure, and volume. Then, of course, the omega is the number of possible configurations the molecules can have for reproducing this temperature, this pressure, and this volume. In black holes, there is an entropy. Do you know the black holes have entropy? That was discovered by Bekenstein, Jacob Bekenstein, Israeli physicist, actually, who was in Tel Aviv until he passed away. I met him in 2012 in a conference in Taiwan, Taipei. The conference was called Horizons of Quantum Physics. By then, I got the best poster presentation. It was like Nature Journal Prize or whatever, together with other guys. One of them is now professor in Waterloo, etc. Waterloo is a nice university because it has the Perimeter Institute. His name is Eduardo Martinez. You can search Eduardo Martinez. Okay. Anyway, Bekenstein discovered that the black holes have entropy. And then after is when Hawking discovered that the black holes evaporate or can evaporate. Still is not sure that that's possible, but the quantum effect suggests that that's the case. But why I am mentioning black holes? Because that's another way to visualize entropy. If you have some surface, let's assume here. In the case of black holes, there's an even horizon. Even horizon is the surface which once you enter, you cannot escape no matter what you do, even if you kill yourself or you do a lot of use the infinite amount of energy. Simply the space-time structure doesn't allow you to escape. That's it. Your future is destiny is go to the singularity and die in a very miserable way because there is no other way to die there, to live, I mean. Then the even horizon is this. The entropy of the black hole is proportional to the area of the even horizon, which is a mystery in physicists because the entropy normally is proportional to the volume of the system. But what I want to remark is that the entropy in this system measures the lack of knowledge we have about the black hole. It means it's the number of possible configurations internally the black hole can have for reproducing the mass, the charge, angular momentum, and is the amount of information we cannot see. So it's for you to realize that entropy is not only a property used in the daily life, also we use to measure the lack of knowledge of the information we have for which we have access from a black hole. Of course, there are many paradoxes. Those who want to study quantum gravity, they always study black hole physics. Going back to more terrenal things, think for a moment, tell me spontaneous processes. Enumerate, tell me at least 2 or 3 spontaneous processes, Spontaneous is that they happen. Exactly. Any idea? Excellent. When you open, using perfume, well, when you do this, it's not so spontaneous. Just you are pushing something. But let's assume that you open the perfume bottle. What will happen? And actually, let's do a parenthesis. Why the perfume? I mentioned that before, but there are many different ways to explain the same thing. No? Why the perfume evaporates again? It has low density, very low density, of course, is you will compare with the air, for example. And of course, the atmospheric pressure is not enough for keeping it contained. No? If you increase the pressure, you can contain it. Because it's a competition of forces. Let's put it this way. You have a tank. Again, I always put a tank. And this is the liquid. The pressure will act against the liquid going out. Then still some particles figure out how to escape. And some particles figure out how to keep here. Okay, and there is a competition. So if you increase this pressure, of course, the pressure starts to defeat the tendency to escape. But we live at atmospheric pressure. At atmospheric pressure, the perfumes are designed precisely to evaporate, because that's why they are smelly. That's why they are smelled. In residential halls, sometimes I take the elevator and some people take shower in the perfume. I don't know. Some guys that you live there, no? You have seen, you enter the perfume. Oh my God, this guy took shower in perfume. Amazing. I don't know. I don't want to say names, but but some guys do that, no? And just smell it is because the perfume is evaporating from you. Once it evaporates completely from your clothes, it stops smelling. There is no more molecules trying to reach your nose. That's it. Of course, it's not that it reaches your nose by purpose. It's that it starts to spread along the whole room, the whole free space. And you have to understand that the molecules collide each other. That collision increases with the temperature. And in fact, now I'm talking to you, and when you are listening, is the vibrations of my voice or the energy I make over the air, and those molecules collide each other and reach your ear. And you should know that the sound propagates different in different gases. If you put the gas of a perfume and you propagate your voice there, maybe it sounds funny. Maybe if the room is just filled from some specific gas, no? Anyway, but I mean, this is what I want you to do. I want you to start to connect physics. When you go in the streets, you start to see a monk falling, you will not be laughing about him. You will say, you apply physics. You say, the guy fell because that's angular momentum, like that. You see 2 collisions between cars, hopefully nothing happened, everybody's alive. You say, conservation of energy, momentum. The forms, that's why the guy survived, because the car could deform and absorb the energy, blah, blah. I mean, you have to apply this in your daily life. Try to do that exercise. You are in the elevator goes up, I feel heavier because blah, blah, blah. The elevator falls, hopefully not, but then for a moment at least, and then you lost all your weight, these kind of things. I mean, the same with thermodynamics. Try to apply. You see a construction, you say, these guys are organizing that building. It looks very organized. They are reducing the entropy of the building, but they are increasing the entropy of the surroundings, and so on. So, I mean, you can apply thermodynamics to in fishes. I mean, here you have Nemo and these guys, you know, and Dory. I don't know how many fishes here. Well, those guys, if you reduce the temperature of the water, of course, what happens? Actually, the fishes can keep themselves the temperature fixed. They can, like the mammals. For example, the reptiles, they cannot. No. Remember that the reptiles are cold-blooded animals. Their temperature depends on the surroundings. Fishes is the same as us. They are not able to what? They can regulate. They cannot regulate. Not perfectly or more or less. Mamahuku, no. Not like us. Not like mammals. Yeah, because the mammals in the ocean are only the whales and dolphins, no? Are the only mammals in the ocean. In the reptiles, well, this is a little outside the topic, but the crocodiles in winter, that's why you can approach and even touch them. They cannot move. They cannot move. Okay, they cannot regulate the temperature. It's not like us that we can fix. And this is a thermodynamic question in biology for you. When the temperature of the environment reduces, just assume I forgot my jacket, my body still keeps the 37 degrees somehow. Why? Exactly, my body has to invest more energy for doing that. I will become hungry faster. That's why in winter you get hungry faster. I don't know if it happens to you. Your body is inputting more energy for keeping you warm. 37 degrees. You cannot reach 35 or 34 because you will die. And you cannot be, well, 40 maybe, 41, 42 is dangerous. That's why the doctor has to decrease your fever by force. They throw you in a cold water by force because it's important to reduce the temperature and until they treat you. Okay, this formula here measures the change of entropy is the heat divided by the temperature. More properly, it's an integral. The change of entropy is more properly as an integral. Well, cyclic no, because that's in a cycle of dq divided dt. If it's a thermodynamic cycle, this is a closed integral. Of course, before the end of the class, I will explain a few thermodynamic cycles which you will see, but not in detail because that's for the next class, together with phase transitions and some problems. And yeah, that's it. We have we explain all about the fundamental laws of thermodynamics. Now let's take a look at possible applications to this. Normally, spontaneously, the heat flows from high temperature to low temperature. We call the hot part source. This is the source of heat because the heat flows from high temperature to low temperature until there's a thermodynamic equilibrium between both, unless you are permanently inputting energy here for keeping this hot, which is how the machines operate. That's why you need gasoline, no? You need gas in your car. You need gas in the planes for the engines to continue working, and the engines operate under thermodynamic cycles. Thermodynamic cycles. Cycle is the change of internal energy zero, but the total work is minus the heat. This is how operates the cycle, applying the first law of thermodynamics to that case. Remember, delta U is the change, or let's put differentially, or let's put like that. plus W. And in a cycle, this is 0. So in a cycle, the heat is minus the work. That's ideally the case. So look at this. This is the principle of an engine. This is how the cars operate, how the machines operate. All the machines you see in your life probably operating under combustion and so on. They operate in this way. There is a hot source. The heat operates here. There is the machines in between. This could be a gas expanding, whatever. It moves whatever here and emits some work. And it's a cycle. What you see here is a series. This is a thermodynamic cycle actually. Because this hot source doesn't go directly to the heat here. It goes here. It makes this camera hot. This expand gas. It moves a turbine here, which generates. It's this way. It's the other way. It goes this way. It moves the turbine, emits work, and then after the remaining gas goes here, and it goes cooler, no, because it emitted some water already. And then, but still, this temperature is still larger than the environment, and it has to be thrown away, and then it goes back. This gas goes back. You receive some pressure here for increase again, and then, if flow again, well, it's not necessary to put some pressure here actually. This is in refrigeration. Here, no. The gas comes here, and again, get some energy, blah, blah, blah. This is a thermodynamic cycle. And later in the next class, we will learn how to calculate the efficiency of cycles, particularly the Carnot cycle, which of course, if we have time, we can mention it here. But for the moment, let's put it this way. Now, what happens if I want to do an inversion here? Do the inverse. I want this heat to go up and this heat to go up. Is it possible? I want the heat to flow from the cold sink to the hot source in the opposite direction. Have you seen that in your life? Refrigerators. The refrigerators, the air conditioners, that's what they do. They extract heat from a place, your room, keeping cool the room, and they throw away. Okay, very hot. That's why you can touch the refrigerator. There's always a part which is very hot, no? Which is emitting the heat to the environment. It's because it's extracting the heat from inside to outside. And the air cons the same. The air cons in winter, what it happens is, in winter, no, in summer actually. What is happening in winter, you don't use a air conditioner for cooling, no? But in residential halls, some people do it. I don't know how can they survive that, but the point is that they extract the heat from the room where you are comfortable, maybe at 20 degrees, and the environment is at 37, 40, and that heat has to go there. Well, how can it go there if the environment is at 40 degrees? Wonder yourself. I don't know if that cycle is here. Let me see if the cycle, in the picture of that cycle. Okay, here, refrigerator. Look at here. We have the picture. I don't have to pay anything. You have to input some work. So now it's not that the work goes out. For this to happen, you have to input some work. That's why the refrigerator has an engine, some motor. These air conditioners also. What is the idea? There is a cycle. I will paint the cycle here. let's assume this is the room you want to keep at 20 degrees. And this is the environment. The environment, let's tell me a temperature of the environment very high without killing people. 30 is too low, actually. That doesn't kill anybody. Okay, 40, like in those countries there, in 45, it will be catastrophic. Maybe in Arabia also. Cristiano Ronaldo playing in 40 degrees there. Okay, let's put 40 degrees there. Normally, the tendency will be the heat to come from here to here, right? Until some equilibrium comes between 40 and 20. Well, at the end will be 40 because the temperature of the environment doesn't change so much because it has many billions of degrees of freedom, which defeat the few degrees of freedom you have here. But then I want to keep this room cold. So I need to extract heat. I need to throw it outside. So I design a thermodynamic cycle. For that thermodynamic cycle, I need to put some camera here. The name of the camera is irrelevant. Let's call the camera A. This camera will have a temperature larger than 40, such that it can throw the heat there. And there will be a refrigeration fluid flowing inside, which doesn't escape. It cannot escape, it's toxic. It's inside the engines, it's inside the refrigerator. You cannot see it, but it's circulating in cycle inside the refrigerator, inside these engines. Then, let's put it like this. There is bomba, a pump here, which input the water. Here, there is another camera. That camera has to be cooler than 20 degrees for extracting the heat of the room. Then let's assume this camera is at 15, well, it's at 20 actually, because that generates the equilibrium. No? But let's put that is initially is at 18. 18 degrees. It has to be lower anyway. Let's put it at 17 degrees or 15. So now the heat can go from the room to this camera. And the cycle is closed here in this side with a bubble of expansion bubble, where the enthalpy is conserved, not conserved. The enthalpy initial is equal to the final, but we cannot say that the enthalpy is preserved constant because you don't know the trajectory of the process. You don't need to know the details, but the point is like this. The liquid here is very hot. Such that let's put that the liquid here is a refrigeration liquid, which actually has low density. If its scale starts to evaporate, before it was discovered that those liquids destroyed the atmosphere and they changed it. Do you remember that there was a crisis with the atmosphere of the Earth in the past because when people destroyed the air conditioner machines, that the liquid, the gas, which the liquid generated, escaped and went to the atmosphere and created a crisis. And you know who discovered that? A Mexican guy. It was a Mexican physicist who discovered that the atmosphere was affected by this thing. I think it was a thesis or something like that. Anyway, there is a liquid here flowing. The liquid here is very hot. Let's put that it's at 50 degrees or something. Then it emits the heat. The heat you collected from the room is emitted here. Then that very hot liquid has to relax. It's at a very high pressure. It's at a very high pressure. So it suffers an expansion here. Very huge expansion, which reduces pressure and reduces its temperature. At the point that the temperature is lower than the room temperature, then the liquid comes here, the liquid comes to the room, extract the heat of the room, which makes it to increase its temperature somehow. But increasing the temperature is not enough. It needs to increase the pressure, and maybe even further the temperature, so it needs a pump here. And the pump makes work, increase the pressure, temperature, etc., up to the point, the conditions necessary to emit the heat. And this is a cycle and repeats and repeats and repeats, and you cannot see it, but this is what happened in the refrigerators. And this is what happened in the air conditioners. If you do the heater, if you change to the heater option, you are exchanging the cameras. Now it's the opposite. But it's exactly the same system. In the case of air conditioners, we don't use efficiency for evaluating how good the air conditioner operates. We don't use efficiency. Efficiency is for the engines, motors. And we compare the efficiency of the motor not with 100%, but with the ideal cycle of Carnot, which I will explain probably in the next session. In the case of refrigerators, we use something called coefficient of operation, COP. It's called coefficient of operation, which it should be larger than 1 if you design it well, the air conditioner. Excellent. This is the cycle I was mentioning. Actually, the proper name is compressor, but it's like a pump. No? But the pump is more for liquids. In this case, probably they are thinking in a gas. But the idea is, it's a liquid or a gas here, internal. They call this camera, do you remember I called camera A, camera B? Well, this is the condenser, this is the evaporator, this is the bubble expansion. I think they invested the cycle because before I put the bubble expansion here, well, it's the same. It doesn't happen. It doesn't matter where you put the things. This is the room. This is the room you want to keep cool here. Here. This is the room we want to keep at 20 degrees. This evaporator, of course, have to be, let's assume 15 degrees. And then when it comes, it has to come here. From here, go here. I inject the work for increasing the pressure and increasing further the temperature, such that this was 40 degrees. I want this temperature here to be 50 degrees, such that this heat can escape. And then when you escape this, the gas or liquid or whatever, lost some energy, naturally, suffer an expansion and reach the conditions necessary to cool down again and repeat the cycle. This is how a refrigerator operates. So in the exam, I can ask you conceptual questions, not necessarily mathematical questions here. Of course, if I tell you, I input 15 kilojoules here of work, I can make a few questions anyway. But what I care is the concept at the end of the day. This expansion bubble is important, and thermodynamically, the enthalpy before the expansion is equal to the enthalpy after the expansion. Remember, the enthalpy is U plus PV, which is internal energy plus pressure times volume. But anyway, the point is that there is a cycle, and we need to input energy because this process is not spontaneous. The process is not spontaneous. If we stop inputting work, what will happen? What happened? No, switch off. Switch off this machine. I don't like. What will happen? This circulation process stop, and then what happens? It will reverse, no? This will start to come inside. The heat will start to come to the room. And at the end, the room will become 40 degrees, which is what happened actually when you switch off the air conditioner in summer. Summer in Europe is very strong. The summer in Europe, summer in Japan also is the hell. It's like, it's so hot that during the nighttime you can feel the vapor coming to you, even at nighttime. So it's like all that radiation accumulated is a start scale at 9. That's the idea. These are some examples. Well, comments before going to some examples, some quantitative examples is the following. Heat transfer, we have to see a little bit of heat transfer in this class, because I think it's very important, because there are many different mechanisms of heat transfer. One is convection, conduction, of course, if you touch two metals. Somebody can tell me why the metals are good transmitter of heat. It's the same reason why they are good conductors of electricity. The free charges also transmit heat. They can transmit it. You remember that you asked that question. You say that the photoelectric effect, there are two ways to move the electrons, the photons heating and difference of voltage. Well, also the heat, The heat also translate charges. So that's the third way. I say two, well, there are third. Right. There is convection is when it propagates in the air. Natural convection is that I heat the air here, and naturally it comes to the ball. For example, when you have a fan blowing a surface, that's forced convection. It means the heat goes to the molecules of the air, and that air escape. Okay, escape. Yeah, actually, I can explain those mechanisms now. And next class, different mechanisms of transmitting heat, because that will complement the session. And next class, I will focus in these quantitative things. In advance, I can tell you that this is a hot ball. This is a thermometer here, and you input the hot ball into the water, and at the end, there is a flow heat from the ball to the water, and they reach a common final temperature. And this is the equation of conservation of energy here. Remember, mass, specific heat, the final temperature is common at the end between all the objects, because they have to reach a thermodynamic equilibrium, and so on. But we will analyze these problems in detail next class. I will stop that part, this projection, for explaining the mechanism of transmission of heat without the projection. So you have to be on the wall by myself, switching off this machine projection. Then, mechanism of transmission of heat. Transmission of heat. Transmission of heat. If I put something hot here, hot, and there is air here, you will feel that the air start to move. The air start to move. That process of moving is called convection. Why it happens? Because when the air becomes hot, what happens with the density of the air when it becomes hot? It's lower, and then it starts to go up, and it's a cycle, no? It starts to circulate the air, until some thermodynamic equilibrium reach. This is called natural convection, because there is no intervention of any machine for the air to move. Now, let's put another example. I put a fan here, fan. The fan is moving and flow the air. It forces the air to move in this direction. And then there is a surface very hot here. I put a plate here at a temperature 100 degrees Celsius. any material. When I put the fan to flow here, these molecules of air will touch. Obviously, the air, let's assume that the air is at a temperature of 10 degrees Celsius, somehow. Then what will happen? One molecule of air, let's isolate one molecule of air. The molecule of air comes here, receive this heat here, and takes it out. And again, and again, and again. So that's why this process is faster. That's when you burn your fingers, you're doing this. Why? It's not because you are crazy, it's because you are using force convention here. It means you are making the molecules of air to take that, once they take the heat, escape, go away, because I want to replace you with a new molecule, which is at 10 degrees and can absorb more efficiently the heat than you. You already absorb energy, get away. I want to replace you for a new molecule. And that's why this is more efficient. This is faster. That's why the surfaces get cooler faster when you blow them. Force convection. And now, of course, there are many things that the air becomes turbulent, blah, blah, laminar fluid, blah, whatever. But we will not go into the details because if we explore every detail, we never finish. The other mechanism popular is conduction. When you touch two objects, I put a metal here, metal. Let's put the metal at 100 degrees Celsius. It's very red. I have a question to you. This is interesting. It touches electromagnetism, and that's why I will ask. Why, when you make a metal very hot, when it becomes so hot, it looks red? Or get some color, gel or something. Why do you think so?
Does it have to do with how quickly the molecules are moving?
What is that?
Does it have to do with how quickly the molecules are moving?
What you see is the radiation in that case. That's radiation at all. And in that moment, that object is emitting radiation of an energy such that is in this visible region of the spectrum. Remember that the spectrum of electromagnetic radiation has some part which is visible, from red to purple. Blue, purple is high energy. Red is the lowest energy, no? Lowest energy. But still, you can see that it's quite hot. Then this, because that's the other mechanism of transmission of heat, which I will mention later, is radiation. Well, let's go step by step. This is conduction. You have the metal, and I put the metal in contact with something at, or let's put better the metal at low temperature, 20, and I put something 100 degrees here in contact. Then what will happen? The heat will flow from here to here, and then the electrons, in the case of metal, because obviously the atoms in the metal cannot move. Of course, the vibrations can move. The vibration propagates, but the electrons move easier, no? So that's why the metals are good transmitter of heat. That's why they become heat quickly, is because they have electrons, free electrons, which propagate the heat more efficiently. But for example, if you put a ceramic, the electrons are not free, so that's why the ceramic doesn't transmit the heat so easily, because it transmits it via other degrees of freedoms, which are vibrations of the molecules and so on. Then in this case, what happened? The heat flows from here to here, and then of course the charges, the electrons or whatever, vibrations start to move. And this is called what we call conduction. Transmission of heat via conduction. Heat transfer part, I will just ask conceptually to you. And maybe we can study the basic law of transmission of heat, but not so complex, not so complicated.
Black body.
Yeah, black bodies and this kind of things. Well, still we will not touch quantum mechanics, of course, because the black body involves quantum mechanics also with the catastrophe, ultraviolet, whatever. But classically. Anyway, this is conduction. The final one, still we have time, we have 10 minutes actually, is radiation. Radiation. So it means if I hit a surface, let's put again a metal here. This is a metal. Temperature is 100 degrees Celsius. 100 degrees Celsius. And I am far at some distance. And let's assume that this camera is empty. There is no air. Let's assume that they isolate. There is a camera here, surrounding, no air. So it's vacuum. This is vacuum. Vacuum camera. If we are in vacuum, we will die, of course. First, we cannot breathe. Second, the pressure is too low. Then explode. Okay. It's the opposite if you go to the bottom of the option, which is people call it implosion. That's what happened to the submarine. You remember that they found it's cruel, but that's what happened. Then, as you are here happily. Okay. And still you can feel some kind of fire coming to you. It's so hot here. Why? Because what you're receiving is radiation. The heat transfer via radiation. That's why the atomic bomb burns you, know? Nuclear bombs and whatever, a lot of radiation. That's why the sun can hit us. It's a lot of radiation propagating in the vacuum, the sun. The electromagnetic radiation of the sun comes through a vacuum. There's no air between the air and the sun, and it still can reach us. That's radiation. So heat transfer via radiation. Heat transfer via radiation is very, very important, particularly because we have these solar panels and many things. No? Anyway, so these are the three mechanisms of propagation of heat. Yeah. And this one, particularly the one touching radiation, is related to electromagnetism. So that's why when you study physics, you study separate subjects, separate topics, but at the end of the day, you start to merge. And you can become a little crazy, but not that crazy. I mean, but when you start to mix things, in the classes, I try to mix a little bit the things, but if I mix it too much, let's say I cannot go so much, no? Otherwise, we become eternal and we will never focus in a single topic. Well, you can see that this is how research is done, actually. When you do research, you start to analyze detail behind detail behind detail, and you can write plenty of papers, results, whatever. So let's summarize this session. In this session, we have seen, I will ask you questions in this final 6 minutes. Zero law of thermodynamics. What is the zero law of thermodynamics?
Temperature and system B is equal to
Yeah, temperature in A is equal to B and C is equal to B, then A is equal to C. Which application does it have? Thermometers, engines in general, when we analyze thermodynamic equilibrium conditions, no? Etc. First law of thermodynamics is conservation of energy. All the energy we were ignoring completely when we analyze the Newtonian mechanics is considered in thermodynamics. Thermodynamics is a subject developed empirically. It's amazing that those guys, they didn't know statistical mechanics, they didn't know quantum mechanics, they didn't know anything, but they could develop it based on empirical trial and error, etc. But this is how science started initially. Second law of thermodynamics, what does it say? No, that's the third law. Well, anyway, the orders of the law, that's correct anyway. If you reach zero, absolute zero temperature, entropy is zero, because ideally, at zero temperature, you only have one possible state consistent with the zero temperature. All the molecules, nothing move. All the degrees of freedom there, quiet. No molecule move. No atom move. Nothing. Like this. And then there's only one possible state consistent with that. As soon as the things start to vibrate and disorganize, then there are many possible configurations internally consistent with the temperature, volume, pressure, and whatever. Yeah. And second law is the entropy. No? The increase of entropy, the entropy of the universe increase. Now, something which I have to mention before continuing the next class is what is the potential for heat transfer? If I want to say, okay, the heat moved from this point A to point B, is because there is a difference in temperature. It flows from high temperature to low temperature. In water, the water flows from point A to B. Why? Because there is high pressure in point A, higher than in point B. That's why the water goes. The same in electricity, the same high voltage to low voltage. And I forgot one more, density. Density. The difference in density is the mechanism of natural convection. Because when you heat a gas, the density becomes lower, and that difference between high density and low density is the mechanism for the air to move. And it happens the whole time. Turbulence in a plane. These turbulence are generated because the sun emits heat, and the heat reaches the air, and the air starts to move. It's part of the reason why, not the whole reason why the air moves, but part of the reason, because there is also Coriolis forces, which we will not see here. There are many other sources of energy which make the air to move and generate at the end turbulence. So guys, for today is everything. Thanks for coming, and let's meet next class then.